Thank you for watching. This paper is about asset pricing models that account for large option panels. In particular, we propose a fast estimation method of models exhibiting latent variables. This includes most of the popular parametric models used nowadays. To make it more concrete, option prices contain information about the underlying asset distribution, such as the skewness, the kurtosis, and the leverage effect. In addition to that, they also incorporate information about risk premia related to the equity, the variance, and so on and so forth. To capture this information, one can use a parametric asset pricing model with a large panel of option contracts. Needless to say that this panel should be diversified in terms of maturity and moneyness. Importantly, the number of option contracts per day have been increasing over the past decades. For instance, over the 1996-2015 period, that is the sample that we consider in this paper, we have more than 120,000 contracts after filtering out the raw data. Considering this large set of option contracts, we could estimate a popular asset pricing model and see what we can learn about risk premia and the asset distribution. Unfortunately, even for models with closed-form option formula, we face a computational issue. Focusing on the simple Eston model and the option contracts from 1996 to 2015, a full maximum likelihood estimation lasts several months on a standard computer. As I will explain in a couple of slides, the computational problem comes from the number of option contracts. Standard solutions in the literature to get rid of this issue consist in restricting the option panel. For instance, we could consider only the option contracts on Wednesday, or focusing on at-the-money option contracts. Another possibility is to limit the sample period. But this restriction approach raises a puzzling question. What is the impact of those restrictions on the financial parameter estimates? Our first contribution has a practical financial impact because it enables the estimation of models with large option panels. In particular, we propose a solution to overcome this computational issue. Our approach saves more than 99% of the computational cost and makes the likelihood estimation feasible. To do so, we adapt the orthogonal particle MCMC algorithm, which enables the parallel but interacting MCMC algorithms. In addition to that, the particle filter that we use is speeded up thanks to a smart interpolation method. As a second financial contribution, we are the first to document the impact on the parameter estimates of restricting the option panel. In particular, we compare estimates of popular models based on restricted option panels with respect to estimates obtained from a large set of option data. More precisely, we compare estimation results when the sample period is shortened, when we impose moneyness restrictions or maturity restrictions. In this presentation, I first focus on the estimation part. The particle filter is typically used to evaluate the likelihood function of a parametric model given some parameter values. For the presentation, I assume one latent variable, that is the spot variance denoted by V on the slide. The particle filter operates sequentially as follows. We start from period 1 and we simulate from the stationary distribution many values of the latent variable. These are the n different spot variances that you can see on the slide. Next, the spot variances are assigned weights according to their fit with the current return and option contracts. The variants that fit best the data are then selected. Then a new iteration starts until we reach the last observation of the sample. So, where is the computational issue? At each iteration, we need to evaluate the option prices for each spot variance. Even with a closed-form formula, like in the Eston model, the computation of one price lasts approximately 20 milliseconds. While this sounds negligible, the evaluation of the likelihood function does last 20 milliseconds times the number of particles times the sample size, which is approximately equal to 278 hours in our case. Note that parallel computation does not solve the problem, even if you have many cores. We propose a solution to overcome this computational issue. At each iteration of the particle filter, we sort the variances in ascending order. Then we evaluate the option prices for some of these spot variances, uniformly taken from the sorted distribution. Next, we use a polynomial function to interpolate the missing option prices. The graphic illustrates the resulting interpolation in red with respect to the true prices denoted in green for one random day taken in our sample. In the paper, we provide a Monte Carlo simulation that shows that our estimation method is accurate. As a second contribution, we use our estimation approach to fit popular asset pricing models. In particular, we focus on well-studied models in the literature that are the Eston model with and without jumps and co-jumps. We document the impact of restricting the option panels when we estimate such models. Our main results are as follows. First, restricting the maturity dimension leads to a dramatic impact on the model parameters. Second, short sample size does not impact too much if the option panel is well diversified. Eventually, some parameters like the persistence and the variance of variance are much affected by the restriction, while others remain stable from one panel to another one. To illustrate the impact of restricting the option panel, let us focus on the Eston model. In blue, we have the posterior distribution of the annualized persistence parameter kappa when we consider the large option panel. By restricting the panel to the at-the-money option contracts, we observe that the posterior distribution does not change much. However, when we only use short maturity options, the persistence parameter is hugely affected. This observation also applies to other parameters, like the variance of variance parameters, for instance. To conclude, estimating parametric models with large option data using the maximum likelihood approach is computationally demanding. We propose a solution that relies on the orthogonal MCMC algorithm and on an interpolation technique inside the particle filter. By ruling out the computational constraints, we are able to investigate the impact of restricting option panels. Among other things, we conclude that the maturity dimension matters more than the moneyness dimension. In addition to that, both dimensions are more important than a large sample period. Thank you for watching.